Just a couple of sample problems using tangency, simple concepts. Let's look at them. Looking at this one right here, and we have two tangents to a circle from the same exterior point. Basically, it's an example of congruent tangent theorem. We have two segments, tangent to a circle from exterior point. What do we know about those two segments? They are congruent. So if this segment is 12, that means this segment right here is equal to 12. Okay, fairly simple. Now let's look at this one. We have a segment US that is tangent to circle R. Okay, we have this segment of that. This half of it is 40 and this half is 40, so the whole segment is 80 long. We know that the radius to this point right here is 30. We'd like to find what x is. Well, if that radius is 30, what do we know about this right here? If we drop a radius right there to that point of tangency, tangent radius theorem says that is a right angle. Well, this radius is going to be the same all the way around the circle regardless of how that circle is drawn. It looks more like a misshapen egg. But anyway, this is going to be 30. This is 30, 40, 50. Oh, that's a 3, 4, 5 triangle, isn't it? If this is 50, what is that? X plus 30 equals 50. X equals 20. So we know that x equals 20. Well, let's look at it a different way. We can use Pythagorean Theorem to solve it a couple of different ways. We could say that this whole segment right here is equal to y. So we have y squared equals 30 squared plus 40 squared. So y squared equals 900 plus 1600. Y squared equals 2500. Y equals 50. Okay, 50 equals x plus 30. And then x equals 20. So that's another way to look at it. Let's look at it even a different way. Let's do it where it's fairly complicated, where we basically come up with x plus 30 squared equals 30 squared plus 40 squared. Now, you're saying, Coach, why in the world would we ever want to do that? We know it's a Pythagorean triplet. Let's just do it that. Well, what if you don't have a Pythagorean triplet? Okay, if you don't have a Pythagorean triplet, you may have to use this in order to solve this thing. Okay, and come up with what it is. So let's go here. So either one of these two ways would work. This right here, if we square that, we're looking at x squared plus, no, not 30, it would be 60. X plus 900 equals 900 plus 1600. The 900s can go away. We need to set that in good old basic form, so we can put it in a calculator. Minus 1600 equals 0. Now, what can we add? Two numbers and get 60, and multiply and get negative 1600. Negative 1600. One is going to be negative, so we're actually going to subtract two numbers. What two numbers can we subtract and get 60, multiply and get 1600? Not too hard to come up with. We'd be looking at x, I think minus 20, and x plus 80. And in this case, we definitely want the x equals 20 part of that, because that's positive and our distances are positive on that. Okay? So that's a quadratic solution to that equation also. Multiple different ways to solve that. Hey, it pays to know your Pythagorean triplets, know what they are. Ooh, wow, that's just simply a 20. You can go with it. Okay, a couple more sample problems. One of them is interesting. The other one is fairly straightforward, not too difficult. It's put a center in here somewhere. Okay, pardon my egg-shaped or misshapen circles and triangles, but let's look at this. Okay, we have the quadrilateral that circumscribes a circle. Okay, a circle inscribed in a quadrilateral. How do we know it's inscribed? Because the quadrilateral is surrounding it. They share points together, but the circle certainly is not on the outside. Is not on the outside of it. Okay, we have points of tangency. If it appears tangent, assume it is, and we're just going to basically apply the congruent tangent theorem here all the way around, and it becomes fairly simple to do. If this is 1, same exterior point, that has to be 1. Same exterior point, that has to be 3. Same exterior point, this over here has to be, whoops, not 3. That needs to be 6. And this over here, this has to be 2. So what's x? Fairly straightforward. Okay? You have some homework, whatever, some other samples where you have to use that kind of concept to create the perimeter of a figure. Now let's look at this. The only thing I can say to you, for you to grasp an appreciation for triangles and circles. Equilateral triangles and circles have very special relationships. Just memorize them. They're very simple to memorize. The central angle. Okay, it's inscribed or circumscribed. Either way you do this, you've got 120 degrees. Wow, I drop a radius right here, or here, or here. I create a 30, 60, 90 triangle. How do I know that? Well, these are 60 degrees. Half of this is 30. Okay, it just automatically lends itself to 30, 60, 90 triangles. It lends itself to this nice little thing here, where we've got a 30, 60, 90, little table set up right here. We've got x square roots of 3, and what's the 90? It's 2x. Okay, so if we can fill that little table up, we can fill up what this does pretty quick. The concept here, if this is 4 here, that's a radius of that circle. Well, the radius of that circle is going to be what all the way around that circle? It's going to be the same thing. So it's 4 right here. Now, one of the things you're going to find out is, guess what? Very special relationship. If I hit the tangent of this right here, we're going to pretend that that's a tangent, I got a right triangle, right? Well, I know this is 30 degrees. That makes this a 60 degrees. Okay? I know this piece right here is 4. So x is 4. What does that make this piece here? Well, I don't even need that piece. I just need this. This is 2x. That's 2 times 4. And that's 8. Well, I know where 4 of it is, so that means this here has to be 4. Oh, wow, look at that. Another very special relationship with equilateral triangles and circles. Guess what? Anytime I have a circle inscribed in an equilateral triangle, the radius and the part outside to the corner of that equilateral triangle is equal. Not true in any other triangle, but with equilateral triangles, this is equal. How do I know? Well, that's the hypotenuse. This is a short leg. The hypotenuse is double the short leg. Okay? It's double the short leg. One of your homework problems, you've got one of these to explore, and you will explore the relationships between these two figures. Both inscribed and circumscribed triangles, circles from both. The relationships go back and forth. Interesting, intriguing relationships just happen in nature. It's one of the reasons they're two of the most stable figures, structures that we have. Okay? I think that pretty well takes care of that. And sample problems. Welcome to Tangents of Circles.